Hi, good morning, everybody. In the last class, we have discussed about these type of problems. So the first problem is limit n tends to infinity log natural log n divided by n, and the second problem we have discussed limit n tends to infinity e raised to n divided by n square. And also we have discussed the solution also, and I think you will be clear about this, and we can show. I'm going to discuss about the next theorem, that is the squeeze theorem for the sequences. Squeeze theorem for the sequences. What will be the squeeze theorem? Very important theorem in this. The statement is given by the squeeze theorem means if there exists some integer n such that an is less than or equal to bn less than or equal to cn, for all n greater than or equal to capital N, and limit n tends to infinity an equal to limit n tends to infinity cn equal to L, then limit n tends to infinity bn equal to L. That is an and bn. If there is a sequence bn such that bn is lies in between this an and cn, and we know the limits of this an and cn. This two into limit sequence, the limits of the sequences we know just are known, and we have to determine this middle sequences limit. Then we can say that if the two end limits are L, then the middle limit of sequences must be of limit L, the same limit L. Okay, this is the last end, final end sequences a cn, and this is the an, the left end sequences. Then in between this bn lies in between this, then this approaches to the same limit as this an and the cn approaches. Okay, this is the SA squeeze theorem, and using these squeeze theorem, we will do some problems also. Some complicated problem. In the case of some complicated problem, we can do this. We can find out the limit using the squeeze theorem very easily. So find limit n tends to infinity n factorial divided by n raised to n. Actually, this is a term an is equal to n factorial by n raised to n is equal to nth term is given by n into n minus 1 into etc. 3 into 2 into 1 divided by n into up to n times n. Right? N given, n get cancelled, and this is n minus 1 by n, 3 by n, 2 by n, etc. Okay. This is always less than or equal to 1 by n. How can you say that this is less than or equal to 1 by n? These all are less than 1 values, because 3 by n by n is 1. So always n minus 1 by n is always less than in between 0 and 1. That is a point something. And when we multiply that point 0 point something to a value, then that will be less than the first value, which is less than or equal to 1 by n. Therefore, 0 less than or equal to an less than or equal to 1 by n. We know that this is limit is 0 and this limit is 0. So, the limit of an must be equal to 0. Okay. This 1 by n into go to 2 by n, 3 by n ഒക്കെ multiply ചെയ്ത് കഴിഞ്ഞാൽ this is ഈ വാല്യൂ എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ n by n മാത്രമേ വണ്ണുള്ളൂ. 3 by n എന്നൊക്കെ പറഞ്ഞു കഴിഞ്ഞാൽ that is always less than 1 ആണ്. Less than 1. n large ആകുമ്പോഴാണ്. ഇപ്പോൾ n 4 ആണെന്ന് വിചാരിക്കുക. അപ്പോൾ 3 by 4, 2 by 4 അതൊക്കെ ലെസ് ദാൻ 1 ആണല്ലോ. അപ്പോൾ അങ്ങനെയുള്ള വാല്യൂ 1 by n കൂടെ മൾട്ടിപ്ലൈ ചെയ്ത് കഴിഞ്ഞാൽ that is always less than or equal to 1 by n. Okay, using that this is always greater than or equal to 0. So 0 strictly less than an, less than or equal to 1 by n. So that's equal to 0. This is 0 strictly less than means this cannot be 0 and factorial is always positive. Positive means strictly greater than 0. So this is type of this. Okay. Next is again we have to use this Tway's theorem. We have to do this problem. Limit n tends to infinity, mod n equal to 0, then the limit n tends to infinity, an equal to 0. Mod n equal to 0 means what? What will be the definition of the modulus? From that, using the Tway's theorem, we can say that this is equal to 0. Next is find the limit n tends to infinity minus 1 raised to n by n. Using the previous theorem, we can do this. What was the theorem? Limit mod n equal to 0 as n tends to infinity. N tends to infinity, mod n equal to 0, then n tends to infinity, n equal to 0. Yes, this is equal to limit n tends to infinity 1 by n. This is equal to 0. Yes. Next theorem, limit n tends to infinity an is equal to L and the function f is continuous at L, then limit n tends to infinity f of an equal to f of limit n tends to infinity an, that's equal to f of L. This is very important one. Limit n tends to infinity f of an equal to f of limit n tends to infinity an, which is equal to f of L. Next example, here using this previous theorem, this is the example. Find the limit n tends to infinity e raised to sine 1 by n. First of all, we have to do sine 1 by n as n tends to infinity. This is 0. How? This is 0. How? Sine 1 by n is always less than or equal to 0 less than or equal to sine 1 by n is minus 1 by n less than or equal to sine 1 by n less than or equal to 1 by n. Or sine 1 by n is always less than or equal to 1 by n. So 1 by n tends to 0 as n tends to infinity. So by Tway's theorem, this is equal to 0. Then use the previous theorem, limit n tends to infinity e raised to sine 1 by n, that is limit e raised to limit n tends to infinity sine 1 by n, that is e raised to 0, which is equal to 1. Okay. Next is very important one, that is the bounded monotonic sequences. Bounded monotonic sequence means a monotonic sequence which is bounded, or a bounded sequence which is monotonic. A sequence having the property boundedness and a monotonic. Okay, then what do you mean by a monotonic sequences? Monotonic sequence means either it is increasing or it is decreasing. A sequence is monotonic means if it is either increasing or decreasing. So a sequence is increasing if a1 less than, a2 less than, etc. And decreasing if a1 is greater than, a2 greater than. First term is the higher value. Next is it is decreasing. Then this is called a decreasing sequence. A sequence is monotonic if it is either increasing or decreasing. Example, show that the sequence is increasing. First of all, I have to take an is equal to n divided by n plus 1. Then we have to, in order to show that this is increasing, an is always less than or equal to an plus 1 for all n greater than or equal to 1. This is we have to do. So n by n plus 1 is less than or equal to, that is we have to show that this is less than or equal to n plus 1 by n plus 1 plus 1. Or this is equal to n by n plus 1 is less than or equal to n plus 1 by n plus 2. If this is happening, if an is less than or equal to an plus 1, an, this is 0 less than or equal to 1. Okay, we have 0 less than or equal to 1. This is it's a right assumption. So the assumption is that this an is always less than or equal to an plus 1. In another way, I think we can do, look the next problem. An is greater than or equal to an plus 1. First of all, we have to show that. Then by solving this, we will get n greater than or equal to, this is n into e minus 1 is always greater than or equal to 1. This is true for all n greater than or equal to 1. So this is decreasing. We can do this in another way also. I will explain in detail in the next video. Okay, thank you.